This is section 2.2 and 2.3 where we're going to approximate the zeros of a function using the intermediate value theorem and also the upper and lower bounds to help find the zeros of all polynomials. So if I give you this problem right here, find all roots of the function f of x equals x cubed plus 2x squared minus 3x minus 5. First thing probably look at is can we factor it, and it'd be a grouping problem and it's not going to work out. You can see in terms of the GCF here, you have an x squared and then an x plus 2 is not going to match up with the 3x plus 5. So we're not going to be able to solve by factoring, but I think it's always a nice place to start as you're doing these problems. And then kind of the next thing is, well, our rational root theorem. We have p over q, so our factors would be plus or minus 1 and plus or minus 5. And as you go and look at each of these values, you'll find out that none of them work. So when we look at f of 1, f of negative 1, f of negative 5, and f of 5, and we look at the graphing calculator or we plug them in, we find out that the remainder on each of these is not equal to 0. So all of our solutions that we have here are not rational. They must be either irrational or imaginary. So then we use Descartes' rule of sign, and I'm just going to give you real quick what the chart would look like. And we find out that it's either 1 positive, 2 negative, or 0 imaginary, and 1 positive, 0 negative, or 2 imaginary. So what do we know from this, or what can we take away from this, is that we know we have one positive real root. Okay, so we know we at least have one that we should be able to find, which also makes sense because if this is a cubic, we know the shape of it will look like this. And so it has to cross the x-axis at least once. So we're always going to have that one real root with an odd degree. So we know we have one positive. So what from there? Well, using Descartes' rule of sign indicates that there are real roots, but there are no rational roots. So we need to approximate the real roots that we do have. And that's what we're going to be doing during this section, is approximating those roots that are no longer nice and easy to find. So we have something called the intermediate value theorem. If a and b are real numbers, such that a is less than b, and you can see on my x-axis where a is less than b, and f of x is a polynomial function, where f of a is not equal to f of b, so you can see on my y-axis they're not equivalent, then in the interval from a to b, f of x takes on every value between f of a and f of b. And so if you think of a polynomial function, polynomial functions are nice smooth curves, there's no breaks in the graph, so therefore it makes sense that it's going to take on every value in between each of these. So every single one of these numbers is part of the polynomial function. Because of this, we can conclude that if f of x is a polynomial function with real coefficients and a and b are real numbers, which is really the only polynomial that we're going to be dealing with, where f of a is less than 0 and f of b is greater than 0, the function has at least one real root between a and b. And so I'm going to draw another picture so we can see that as well. So now, as I've graphed this second one, f of a is less than 0. So now I have the y value less than 0 on this point, and then f of b is greater than 0. I made sure that one was greater than 0. And so now what we can conclude from this is if I now draw a smooth curve through these 2 points, you will notice that it has to, using the intermediate value theorem, it must intersect the x-axis between a and b somewhere. And so therefore we at least have one real root, which means we can therefore approximate it. Alright, now we have one more thing to talk about before we start approximating these real roots, and it's the upper and lower bound rule. So a real number b is called an upper bound for the real roots of a polynomial function if no zeros are greater than b. So we're going to find where there are no solutions or no zeros that are greater than that value. It is also a lower bound if there are no real zeros less than b. So we're going to find an upper bound where the graph does not cross any farther past that one, and then a lower bound where the graph does not cross the x-axis any less than that value. So how do we find these values? The upper and lower bound rule. Let f of x be a polynomial function with real coefficients and a positive leading coefficient. So if all this stuff is true, we're going to divide f of x by x minus c using synthetic division. So if we're doing an upper bound, we're going to pick c values that are greater than 0. If we're looking for a lower bound, we're going to pick c values that are less than 0. If we're looking for the upper bound, if c is greater than 0 and each number in the last row is either positive or 0, c is what we call an upper bound. For a lower bound, if c is less than 0, the numbers in the last row are alternating positive and negative. Remember, 0 counts as positive or negative in this case. If that is the case, c is considered the lower bound. So that's how we can take the x-axis and shrink it so that we're only focused on a certain section of the x-axis as to where that graph can actually cross, so we can approximate those zeros. So to kind of show you a quick example, if I have a graph that looks like this, on the x-axis, you can see where it crosses the x-axis. To the right of 0, somewhere to the right of that last value where it crosses, we're going to have the upper bound. And then somewhere to the left of that last point it crosses the x-axis, we're going to have the lower bound. So this will be x equals some value of c, and over here will be x equals some value of c as well. So that's the upper and lower bound. The graph will not cross past that point again. So in this example, we're going to find the upper and lower bounds for the function f of x. So we'll start with the upper bounds. So we want to choose values that are greater than c. Okay? So we just greater than c, I'm sorry. So in this example, we're only looking for the upper and lower bounds of the function. So let's start with the lower bound. So we want to choose values that are less than c. So we'll start with -1, and we'll go from there because we want to find the least lower bound that we can. So if we start at -1 and we do synthetic division, we have 1, -5, 3, and 2. Now remember, these should alternate positive and negative. So if I carry down the 1, then I get 1, and then I multiply to get -1, add those to get -6. So positive, negative, so far it looks good. That'll give me a positive, positive, negative, positive, and then the next one we hope to be negative, and in this case it just so happens to work out the first time. Positive, negative, positive, negative. So therefore the lower bound will be at x equals -1. And you shouldn't just say it's at -1. Tell me what we're talking about here. We're talking about the x value on the x-axis. So x equals -1 is the lower bound. Now let's go ahead and look for the upper bound. So let's do values that are greater than 0. Once again, starting with 1, we're going to use synthetic division. And we want all positives here. And we can have 0, but we need all positives. So I notice on the second term I get a negative. Okay, so we can't use 1. If I use the next number up from 1, which will be 2, and you do the same thing, you're going to notice that you're still not going to get a positive number there. So recognizing that the next number that really is going to give me a positive has to be right here, needs to be a 5. Well, to do that, this number over here would need to be a 5. Carry down the 1, 5, that will give me that 0. So I don't have to do 1, 2, 3, 4, and 5 to get to that. If I make that connection there, I can go ahead and jump right to 5. And right now I know I'm going to get a 0. So we're good, and then we can continue on, and we find out that we will get all positive numbers or 0 for x equals 5. So the upper bound is at x equals 5. So what this indicates is the graph will only cross between these two. So it might go up and do something like that. It might go up, come back down, and then go back up. But those zeros are only going to be between -1 and 5. So on this last slide here, find the roots of the function, and we're going to approximate these. So this gets back to the very first example I gave you where we realized that there were no rational solutions. By graphing it, you can see that it looks like it's going to cross 3 times, 1, 2, and 3. And you can kind of see what that upper and lower bound is. But when you go to calculate, it might look a little different. We just know that it's going to cross nowhere again after, it looks like x equals 1 something, and then x equals maybe -2, -3 something. So we can find the upper and lower bound. That'll give us a starting point, and then from there we'll kind of break it down to find out what two numbers it's actually in between. So let's go ahead and do the upper and lower bound again. So why don't you pause the video right now and go through that process and see how you do. So you can now see how I did the lower bound. I've tried -1 and it did not work because I got 1, 1, and with lower bound we're trying to get positive, negative. Then I did -2, and it worked for the first two, but then not the third one, and then I did -3, and you can see positive, negative. 0 counts as either, so my lower bound is x equals -3. With the upper bound, I chose 1. Start with that, go from there. I almost got it up until the end I had a negative. Don't decide to jump to 3 or 4 just because you have a negative there. Try 2, which I did, and then now I get positive. So my upper bound is at x equals 2. So what do we take away from that? Well, we know that the solutions of this cubic are going to be between -3 and 2. So we want to find what consecutive numbers they are between. So the way that we're going to do this is we're going to use what that y value is. So you can see here on the graphing calculator, I plugged in the function, and then I looked at my table. And looking at the table here, so you have -3, that was my lower bound, and then 2 was my upper bound. So we're going to use that to kind of show where the graph is crossing the x-axis. So to write this out and to kind of show your work as to what I want to see is that f at -3, what is that equal to? -5. When you plug in -2, what is that equal to? 1. And go all the way from your lower bound to your upper bound. And so f of -1 is equal to -1. F of 0 is equal to -5. F of 1 is equal to -5, and then f of 2 is equal to +5. So what are we looking for here? Remember the intermediate value theorem. When you have a change in y from positive to negative, it must cross the x-axis because your positive and negative are changing. So that's what we're looking for here. So as we plug in these values, look at the y value. From from -5 to 1, it goes from negative to positive. So we know we have a 0 right here. From positive to -1, we also know there's a 0. Now the next one goes from -1 to -5, so there's no change in terms of the sign. The next one, f of 0 and f of 1, go from -5 to -5. Once again, no change. And then from -5 to 5, we have another change. And realize what is happening here. If you are at -5 and you go from -5 to 5, the graph has to cross somewhere in between there. And so that's what we're saying is that that's where the 3 zeros are located in between those specific numbers. So now we know what numbers they are between in terms of the zeros. We know they're between x equals -3 and x equals -2. So the 0 in terms of where it crosses the x-axis will be -2 point something. We know that it's been between -2 and -1, so this will be -1 point something. And then between x equals 1 and x equals 2, which will be 1 point something. So if we want to just approximate in terms of consecutive numbers what they're between, we have them. So here, here, and here. And remember, don't give me the y value. The y value is the output. We want to know where the x value is. We're solving for the zeros, which is what is x when y is 0. Okay? So let's take this one step further. Let's go ahead and round to the nearest tenth. Okay? To do this, though, we're going to use the calculator to make this a little bit easier on ourselves so we don't have to keep plugging in numbers. So on your calculator, look at the functions on top. Above window, it says TBL set. That's table set. So we want to go to table set, and that will bring up this menu. And so when you look at table set, you want to start your table at one of the two x values. I just happen to start it at -2. And then you want to change your table to increments of 0.1 because we want to round to the nearest tenth. So once again, change your table set to table start at -2, and that's one of the x values. And then change your table to 0.1 because we want to round to the nearest tenth. Once you do that, you want to look for that change, just like we did over here on each of these when we went from a negative to a positive. So you can see right at -2.4 and -2.3, we go from a negative to a positive. So we can round this to the nearest tenth by indicating that's where the change occurs. And once again, because you're going to be doing this on your calculator, you want to show me that. You want to say at f of -2.4, that is equal to negative 0.104. And then at f of negative 2.3, that's at 0.313. So knowing that, when we go to round and I want to know what it is to the nearest tenth, which one are you going to put? Negative 2.4 or negative 2.3? Well, you want to write the one where it is closest to. So which one of these y values is closest to 0? This one. So therefore, because it's 0.1 compared to 0.3, so therefore x is approximately going to be negative 2.4. So x is approximately negative 2.4. And that's what I'll be looking for. And so you can do this on all three of your zeros. So you can see, once again, as we look between negative 2 and negative 1, your table start, we started at negative 1. Still the table change is 0.1. Take a look at your table and find where the change occurs from positive to negative. And so on this one it's negative 1.3 and negative 1.2. So once again, to show that, you're going to say f of those two. So f of negative 1.3 is approximately 0.083. And then f of negative 1.2 is negative 0.248. So which one is it closer to in terms of the nearest tenth? Well, 0.0 is closer than 0.2, so therefore x is equal to negative 1.3 approximately. And then the last one I'll show you as well. So once again, we started the table start at 1, which is this one, and the table change is still 0.1. Took a look at the table, look for the change in your y value from negative to positive, so we know what's crossing the x-axis at that point. So somewhere between 1.6 and 1.7. So f of 1.6 is equal to negative 0.584, and f of 1.7 is equal to 0.593. So these are both at 0.5, so we have to go to the next one over, which would be 0.58 compared to 0.59. So therefore, round to the nearest tenth, x is approximately 1.6. So that's how we're going to show our work, because we're going to be doing a lot of this on the graphing calculator. That's how we're going to show our work, to show what consecutive numbers the zeros are between, and then to take it that step further and find it to the nearest tenth. So that's what we're looking for. We'll talk more about it in class if you have questions about what kind of work you need to show. Because like I said, you're doing a lot of this on the calculator, but knowing how to use the calculator and also show where those change in y occur.